The next equation that we need to consider in our development of fluid dynamics is Poisson's equation. And Poisson's equation is an equation that relates the mass and the gravitational potential. Many of us have seen Poisson's equation before. Let's just see how we get to it. So I want you to consider a surface of a volume. Again, the surface has some area, unit area, ds. And let's have, instead of having a uniform density, let's just have a point mass, a mass at point P. And that subtends a solid angle, d omega, of the surface, which is defined by ds dot r over r squared. So it's a point mass of mass m at point P, surrounded by a surface S. Now, the gravitational acceleration, we all know, is g is equal to minus the gravitational constant times the mass m over r squared r hat. And we can go from there to say that the gravitational acceleration dotted with that surface element ds is just minus g times the mass of n times this delta d solid angle. Now, if we integrate that over the surface, then we have minus 4 pi g times m. And these should all look fairly familiar. So now let us replace m with a density rho in volume v. So now we have an integral over the surface of the gravitational acceleration dot ds is equal to minus 4 pi g times the integral over the volume rho dv. And we know from the divergence theorem that the integral over the surface of g dot ds has to be equal to the integral over the volume of the divergence of the gravitational acceleration integrated over that volume. So that's the divergence theorem. And so it follows then that the integral over the volume, the divergence of the gravitational acceleration, plus 4 pi times g rho, all of that times dv, has to be equal to 0. And finally, recall that we defined g as minus grad psi, or equivalently, we've also described it as minus grad phi, but either way, psi or phi, both are the gravitational potential, and the gravitational acceleration is just simply the gradient of the gravitational potential. And so for any volume, we have the result that gradient squared of psi is equal to 4 pi g rho. And that is Poisson's equation. Derived fairly simply. Now we're going to put together Poisson's equation with our continuity equation and Euler's equations in order to make the final steps towards understanding our system. So we so far know we have three equations for fluids so far. And those equations are d rho dt, these are all in Eulerian format, plus divergence of rho u is equal to 0. And that one is the continuity equation. We have the equation that we developed from the conservation of momentum, that rho du dt, partial derivative of the velocity field, plus rho u dot grad u is equal to minus grad p minus rho grad psi. That's just a slightly different rewriting of the Euler's equation that we've written out before. And we have finally the equation that we just derived, grad squared psi, which is equal to 4 pi g rho. And that's Poisson's equation. So we have three equations. The first two can be combined and along with the third one, and we have four unknowns. Those four unknowns are the density, the velocity field, the pressure, and the gravitational potential. So in order to close this system of equations and relate, for example, P to rho, we need an equation of state. To relate P to rho. Because the first two equations allow us to solve for P, and we can bring in the gravitational potential, but we're limited to either get P or to get rho. But if we can bring in an equation of state, that will allow us to solve the full set of equations and to completely describe the system. And that's what we'll work on doing in our next lectures, is to bring in this equation of state for this system.